and running, I believe. So let's get our feet on the ground with what these atoms are and what elements are, how this all fits together. Structure of the atom. All right, so Dalton, and like I said, we're going to cover some of this, but the purpose of this exercise was to kind of get you digging into this a little bit and connecting with it at some point. Dalton's atomic theory. A new system of chemical philosophy, 1808. That's his book. So he writes a book. Much of his theory is still regarded as correct today. So he's saying that elements are made up of atoms, and the atoms of one element are different from the atoms of another element. This is what differentiates one element from another element, are their atoms. And he's right. Every one of those elements right there has a different atom. It's got the same basic structure. We're going to look at what this basic structure of an atom is, but each one of these elements has a particular structure. And it's different from another element. And elements combine with other elements to form compounds, and they combine on an atomic level. So if this was hydrogen and this was oxygen, you would be getting water molecules that have two hydrogens and one oxygen, H2O. That's a compound. All right? But, well, what I said, a chemical reaction does not convert one element into another element. Hydrogen, hydrogen. Oxygen, oxygen. All right? Every element that goes into a reaction comes out of that reaction as that element. Now, it may have been changed. It may become an ion. It may have gained or lost some electrons, but it is still hydrogen. It's still oxygen. You cannot convert one element to another element by a chemical reaction. Those are nuclear reactions. Uranium undergoes nuclear reactions that will change the uranium to a different element. But that's not a chemical reaction. So then here's his postulates. Here's 6 of them, I guess. All matter consists of tiny particles called atoms. An atom cannot be created, divided, destroyed, or converted to any other type of atom. Atoms of a particular element have identical properties. Atoms of different elements have different properties. Atoms of different elements combine in simple whole number ratios. Chemical change involves joining, separating, or rearranging atoms. Now there's an asterisk here on number 6, on number 5, number 4, and number 1. And saying that these postulates are still regarded as true today. Now 2 and 3 were pretty good postulates given what Dalton had available to him. He did not know about nuclear reactions. Number 2, an atom cannot be created, divided, destroyed, or converted to any other type of atom. We have atomic bombs. We have nuclear reactors generating electricity. This is all something that was just way beyond anything Dalton could imagine at that point in time. But that's nuclear reactions. By a nuclear reaction, you can convert. And then what he didn't know, and actually even Bohr and a lot of people didn't know even into the early 1900s, that there are neutrons. There's a third particle floating around in there. No, it does not, neither positive or negative charge. That's what made it the hardest particle to discover. the fact that protons are positive, electrons are negative, they responded to magnetic fields and different things like that. There were certain things they could do in a laboratory that actually showed that. But neutrons were kind of elusive for a while. And that is where we get the concept of isotopes. There's carbon-12. Well, we'll get into isotopes, but just log that away. I don't want to go on a tangent there. So that's Dalton, the father of the atomic theory. He's taking it out of alchemy and now taking it out into science. He wasn't interested in making gold. He was interested in understanding the weather and the gas in the atmosphere, and he was interested in understanding things. Okay? So he starts probing into what is this world and how does it function? And he did some pretty good thinking. See, he couldn't be texting. He wasn't texting on his cell phone. He was actually thinking. And he was thinking deep thoughts. Gold foil experiment. Where's Rutherford? What happened to Rutherford? No, J.J. Thomson. What happened to J.J. Thomson? I can't believe it. I must have gotten the wrong set of slides or something. I'm disappointed. We got to get to J.J. Thomson. I don't know why he's not in this set of slides right here. Okay, well let's. Well, I'll just have to tell you about J.J. Thomson. So we get past here, and here's the situation that was going on. People were working with cathode ray tubes. I did have a slide on this, and they would have an electrical field in here. This would be a vacuum, and they'd have an electrical potential across here. And what they would find is a beam and they put a fluorescent coating in here, like a fluorescent light. They put a fluorescent coating in here, and they would see a beam, some sort of a beam, going from the negative to the positive. And this is a cathode ray tube. Okay, now let me just tell you what a cathode ray tube is. Do you remember the fat TVs? The old style TV? That wide? Not flat screen TV. Those are cathode ray tubes. That's what they are. They got a fluorescent screen. They got a fluorescent thing on the front of the screen. They have got an electrical field in there, and they're firing electrons to the front of the TV. And they're creating images electronically on the front of the TV. That's a cathode ray. Now, this is happening in like the 1890s. So this is before we even knew what a television was, okay? But they're starting to work with these beams. And then what they did is they created a magnetic field here. They created a magnetic field. They're firing the beam through there. They created this magnetic field, and what did they see? The beam bent towards the positive plate. Whatever it is, it's negative. We don't know what that is. This is a big question mark. What is that? It's negative. Whatever it is, it's negative. And Thomson, J.J. Thomson, is the one that said, because it would change this copper, iron, to still get the same beam. Same beam. What is this thing? It seems to come out of almost anything we put in here. So he called it corpuscles, and the corpuscle was renamed electron. Electron. So he's saying it's a particle, and it's a negatively charged particle, and it's coming out of the atom. It's subatomic. All right, so he has this picture of the atom being this, it was the plum pudding model of the atom. The atom is kind of like the pudding, and it was positively charged. Where did he get that? Well, if there is a negative particle that is coming out of the atom, and the atom is neutral, then there must be something positive in there to balance out this negative. Follow me? So without any real evidence for a positive particle, he proposed we're going to find some positive nature to the atom to balance out this negative particle that exists in it. So J.J. Thomson's real claim to fame is proposing and discovering the electron. I mean, everybody was seeing these cathode rays. So all around the world, they're doing this experiment and seeing this. Thomson is the guy that says it's a negative particle coming out of atoms. And we eventually called that electrons. All right, so I'm trying to give you a flavor for the history of this development so you could see that people had to wrestle with what they are observing. They're observing something new that no one's ever seen before and trying to figure out what it is. What's going on here? What is going on here? And it's not like they saw it on Saturday or Friday, got a good night's sleep, woke up Monday and had the answer. They wrestled with this for a while, for a long time. What are we seeing here? I don't know. People were speculating different things. So the next key one is Geiger, Marsden, and Rutherford. Geiger and Marsden are working with Geiger counters. This is a radioactive substance in here that's emitting alpha particles. Alpha particles are positive particles. They're positively charged. They're actually like helium nuclei. They didn't know what they're dealing with really at that point in time, but they knew they had a kind of a powerful positive particle. And they said, okay, well, let's get some gold, and they're not alchemists here, but they said, let's get a heavy metal like gold, pound it into a very thin film, as thin as we can get it. So maybe it's only 10 or 12 atoms thick. I don't know how thick it was, but they tried to get themselves as thin a film of gold as possible. And now they're still working on what Thomson gave them. So what are they assuming? They've got their gold film, and they're assuming that what they have is a pretty even film of mass of gold. All right? It's just kind of the mass of the gold is just evenly out through that film. And they're going to fire alpha particles at it. Big, heavy particles. So they're thinking, well, the alpha particle will probably, go through the film. And they put a detector. This is a detector out here that went like the Geiger counter. When an alpha particle hits it, it gives off a little electrical impulse. So this is the forerunner of the Geiger counter. It's a detector for alpha particles. And so they could have just put the detector right here, that far. And because they weren't expecting it to do much more than just go right through the film or get deflected a little bit as it went through a thicker portion of film versus a thinner portion of film, whatever. They was expecting most of the alpha particles to bombard this portion of the detector. But they said, well, let's just wrap it all the way around. Okay, wrap it all the way around. So they did that. And bam, I could see Geiger coming into Rutherford and saying, I think we did something wrong. Why? Well, some of the alpha particles almost came right back at us. Something's going wrong. And so they did the experiment again and again and again, and they kept seeing some of the particles almost coming back at them. And so Rutherford either got a couple good night's sleeps, I don't know what, and he said, no, this isn't what we've got here. What we've got here is this. We've got concentrated areas of charge and mass, and we have a lot of empty space. Most of our gold film is nothing but empty space, separated by areas of concentrated mass and positive charge. And when our alpha particle hits, kind of directly hits one of those, bam, it comes back at us. You follow me? This is the thinking. And so he called these, he said, this is the nucleus of the gold atom. These are the nuclei of the atoms, and the electrons exist out in the space around those nuclei. They're much smaller. They have almost no mass. So other than a little electron now and then, there's empty space. It's like our solar system. We've got a sun and 9 planets, 8 or 9 planets, depending on how much you want to argue about Pluto. All right? We've got a solar system with the sun and a certain number of planets, and what? A lot of empty space. Pluto is billions of miles out there. And so if you arced out Pluto, what do you got in the solar system? A lot of empty space. Lots. And here are a couple little planets every so often. They said, hey, that's what we kind of got, what we have here with the atom. All right? So that's where this came from. If they had not wrapped this around here, they would have missed the most important part of this experiment, that some of the alpha particles came back at them. The quote they had is that it's as if we fired a cannon at a piece of paper and the cannonball bounced off and came back at us. That's what they were looking at. There's like, how did this happen? How did this happen? Well, we're not firing it at a piece of paper. We're taking all the mass of that paper, all the mass is being concentrated down into tiny little spaces, which is the nuclei. So this is early 1900s. And then along comes Bohr. Let's look at emission spectra. First, you need to know what we're talking about with spectra. The electromagnetic spectrum is a broad range of things of different energies. All right? Radio waves. You turn the radio on in your car. You know you got radio waves. You're receiving radio waves. They're not hurting you. Why? Because they're very low energy. They're very long wavelength. Very long wavelength wave. These are all traveling at the speed of light. Radio waves, microwaves, infrared, visible, ultraviolet, X-ray, gamma rays. They're all traveling at the speed of light. What's different about them? Some of them have a very long wavelength, so they're very low frequency, low energy. Some of them have higher wavelengths, or shorter wavelengths, higher frequencies. More waves are going by you per second. Higher energy. But all of these are are below the energy of chemical bonds, even visible light. But as you start venturing into ultraviolet light and X-rays and gamma rays, you're venturing into the energies that are comparable to the chemical bonds that hold things together. And so there's enough energy there to bust those bonds. That's why we talk about ionizing radiation. Ultraviolet, X-ray, and gamma are ionizing. It can break chemical bonds and harm you. But that's how they do harm you, by breaking chemical bonds. Your body likes the chemical bonds it has. It likes to form its own chemical bonds, and it doesn't like things interfering with the way it's bonded together. And these things interfere with that. All right, well, we're going to look at visible. So here's the visible spectrum from red to yellow to green to blue, purple, violet. Violet is higher energy. All right, so the point here is that every one of these colors, every color in the visible spectrum represents a certain energy. Okay, that's the main point. Every color is a particular energy. So then in the early 1900s, late 1800s, early 1900s, they're experimenting with some other stuff. They're taking tubes, filling them with certain gases, putting a voltage across them, which energizes those gases. And then looking at what happens. They're getting light. Light's coming out of there. You know, oh, okay. Well, let's pass it through a prism and see what kind of light this is. Is it a continuous spectrum of light? A continuous spectrum of energies? No. Hydrogen gave 4, and we can't see that there. Can you turn this light off for a second, please? There's this light, green, there's a blue and a violet. You see those? Those are kind of hard to see on a black background. That would be neat to improve on this. Put some other kind of background. Couldn't be red background, but would need some other kind of background. Gray, maybe, so we could see these 4 lights. All right, so I'm saying, wait a minute. We're just not getting a kind of a continuous range of energies. We are getting 4 specific energies of light being emitted from hydrogen. Where's this coming from? Again, dozens of people are doing these experiments and thinking and proposing explanations. But Bohr hits the nail on the head. Bohr said, here's what I think's happening. And this goes along with what was written down here this morning. That the electron, here's your nucleus. Okay, they kind of understand we got a nucleus, we've got electrons outside the nucleus. What is going on with those electrons? Are they just randomly bouncing around out there? What are they doing? And Bohr said, no, they're not doing that. They are in particular energy levels. So the hydrogen, before they put them in that tube, they're just happy and they're at a nice relaxed state. The electron, there's only one electron in hydrogen. So there's just one proton here, one electron. But when we put it in the electronic field, it excites the electron up to another energy level, or 2 or 3 different energy levels. And when the electron relaxes back down to its natural state, its ground state, it emits a wavelength of light. What wavelength of light? The wavelength of light that corresponds to the difference between these 2 energy levels, the energy difference between them. That's what's being emitted. So that's why it's emission spectra. It's the energy emitted when the electron relaxes back down from an excited to a ground state. You with me? You following this? Okay, so this is Bohr. And he's saying energy isn't a continuum of energy, it's quantized. The quantum, there's a quantization of energy. Energy comes in certain little packets of energy. There's an excited state, so that electron is in an excited state. There is a ground state. What's that? The electron in the lowest energy level that is available to it. That's its ground state. It falls down, but it doesn't fall into the nucleus. It falls into an energy level. All right, so he referred to these as orbits, like the Earth is orbiting around the sun. He referred to those energy levels as orbits. All right. And I didn't have us go any further than Bohr. Bohr is in the early 1900s, 1900, 1915 time frame. Around then also comes Heisenberg and Schrödinger. And they didn't, don't get the impression that they throw this out. We're not going to throw this out. We do view the electrons in the atoms as in principal energy levels. So did Heisenberg and Schrödinger. But they said it isn't this simple. It's not quite this simple, that the electron just is in this distinct orbit. Heisenberg came up with Heisenberg's uncertainty principle. He says, I could tell you where that electron is, but I can't tell you how fast it's going. Or if you ask me how fast it's going, I can tell you how fast it's going, but I can't tell you where it is. I can't tell you those two parameters about it simultaneously, position and speed. There's an uncertainty about where exactly what that electron is doing and how it's moving. So that was the Heisenberg uncertainty principle. Schrödinger's equation then gave rise to, so we went from orbits to then also thinking of so we got energy levels, sub-levels, orbits, orbitals, and then the spin on the electron that Schrödinger's equation gave to us. So there's the plum pudding model. The atom is kind of uniformly mass positive with negative particles embedded in it. Rutherford came to the nucleus with electrons out there, and now Bohr is fine-tuning our understanding of how the electrons are behaving. So there's the Rutherford model. Here's the Bohr model. Okay, so, and you have seen emission spectra. Neon lights. What are neon lights? They're lights like that have neon in them. They're filled with neon gas. They're filled with neon gas, and a voltage is put across them, and they emit light. What light do they emit? The emission spectra of neon. Here you're looking at the emission spectra of argon, krypton, xenon, helium. All right? That's emission spectra. And then another place where you have seen emission spectra is in fireworks. You go, oh, look at that green one. Oh, look at that blue one. What is that green one? The green one, barium salts packed into the dynamite. Fired up there, and it explodes, and what's it doing? It's exciting the electrons in the barium to higher energy levels, and as they relax down, they release a green light. Copper, blue light. Strontium, red light. Sodium, yellow light. So every element has its own particular emission spectra. This has given rise to an analytical technique. You can take something unknown, you can take a little platinum wire, a little coil, dip it into the stuff and put it in a flame, and look at the flame will change colors. There'll be different colors depending upon the different elements that you put in the flame. And you can actually develop an emission spectra analytical technique, which is used. If you got an unknown, you say, tell me what elements are in there. Well, let me get the emission spectra. I'll burn it, and we'll analyze the colors coming out of it. All right, so let's take a look at this. So here, if we put it all together, this is where we get to. That we've got a nucleus. We've got a nucleus. At the center of the atom, there are protons in it, neutrons with no charge, and then there are electrons. Negatively charged particles spinning around the nucleus. So here's our nucleus, protons and neutrons, and then the electrons spinning around it. And we've got these energy levels. So N equals 1, that's your first energy level. N equals 2, that's your second energy level. N equals 3, third energy level, fourth energy level. And you will see we'll go up to the fifth, sixth, and seventh energy levels. I'm kind of wondering here if... Oh, okay. I'll tell you what, I'm just kind of looking at the time. So on, today's Tuesday, on Thursday, I'm not going to finish right now. I just want to mention one other simpler concept for a minute, and then we'll do a deep dive into this on Thursday. So Thursday we're going to pick up with this and understand what this is and how to start constructing electronic configurations of any element. All right? So how does this go to electronic configurations? But for today, let me just introduce this and get you familiar with what this is. Okay, this is just a nice, good, clear way of describing an atom. And we have this atomic number, mass number, charge, symbol. So let's take let's take sodium. Let's look at the sodium atom. See, it's Na up there, sodium. Can you turn the light back on? Let's just look at sodium. So if we want to look at sodium, we're going to put the symbol right here. And that number 11 is the atomic number. What is the atomic number? The atomic number equals the number of protons that are in a sodium atom. That's the most important number about sodium. And so we put the atomic number right there. Atomic number. And then up in here, so that's the atomic number, we've got the mass number. This equals the number of protons plus the number of neutrons that are in the nucleus. In addition to protons, there are usually neutrons. Hydrogen would be the exception. The most common hydrogen atom is one proton and one neutron, one proton and one electron. That's it. It's a hydrogen atom. But everything else, helium is going to have some protons and neutrons. So the mass, that number underneath sodium is the average atomic mass. But let's say that the mass number for this isotope of sodium is 23. That's the mass number. So what that means that this has 11 protons, but how many neutrons does it have? 12. How are you getting that? Okay. This is protons. This is protons plus neutrons. Right? So if we subtract that, it's just simple math, subtract this number from that number, we're getting rid of the protons. And it has 12 neutrons. Yes? So that's how you get the number of neutrons. This would be the sodium 23 isotope. What's that mean? Well, let's look at another isotope of sodium. Let's say I write this symbol down here. I'm not changing that number. That is sodium. Any atom with 11 protons in it is a sodium. Any nucleus with 11 protons in it is a sodium atom, or ion, or some form of sodium. This is what characterizes sodium. You can see we go down to neon, it's number 10. You're never going to see a neon with an 11. That's sodium. Follow me? This is the most characteristic number of an element, the number of protons that are in its nucleus. That will never change, except for a nuclear reaction. So this is the sodium 22 isotope. So there are isotopes. Okay, now let me, and I'm not putting anything up here. This position is blank, so there's no charge on this. So we're talking about a sodium atom. We're not talking about a sodium ion. An ion is a charged particle, positive or negative. We'll figure these things out. But if you see nothing there, then it also has 11 electrons. This thing would have, if we really knew it now, we have nothing here. So we have 11 protons, we have 12 neutrons, and we have 11 electrons. How do I know I got 11 electrons? Well, that is plus 11. Every proton has a plus 1 charge. The overall charge is 0. How is it going to be 0? It has to have 11 electrons. It has to have an equal number of electrons to balance out every proton, and therefore 0 net charge. The overall charge is neutral because the protons equal electrons. In the atom, protons equal electrons. Okay, so let's see if you're grasping this. Let me put up a couple isotopes of carbon. Tell me the number of protons, neutrons, and electrons in each one of these. 6 protons.
6 neutrons. And 6 electrons.
All right. How many protons?
6, 8, 6.
6. All right. This would be this is carbon 14. This is the carbon 14 isotope of carbon. It exists. You've heard of carbon 14 dating? That's not a dating website, okay? That's a technique for trying to determine the age of something based on how much carbon 14 isotope remains in it. Carbon 14 dating. All right. Well, one that we're going to be looking at for a way of doing some calculations here, there are, in nature, if you extract chlorine out out of the environment, out of the Gulf of Mexico, which is what Dow Chemical did 70 years ago or so. They came down there and said, okay, let's see if we can extract chlorine out of the ocean. And they started extracting chlorine. Well, they get some of this and some of this. These are the two naturally occurring isotopes of chlorine. So let's do protons, neutrons, and electrons. For this one. And this one. 18? Yeah? 18 plus 17 is 35, or 35 minus 17 is 18. 17. This is the carbon, this is chlorine 35. And this is chlorine 37. Isotope. Those are the two isotopes. What we're going to find, about 75% of the chlorine in the universe is this isotope, and about 25% of it is this isotope. Okay? Let me see something here. Yeah, these things will show up in your Chapter 2 homeworks. This is just a little worksheet. I was just kind of looking at it to see the value of giving this to you right now. I'll hand this out at the beginning of class on Thursday, and then we're going to do this worksheet in class, which really is going to, so if you want to read up something, be familiar with something for Thursday, look at electronic configuration. How do you determine the electronic configuration of atoms and elements? And we'll do some exercise, we'll explain it and do some exercises in class to really highlight the significance of that as we move forward chemically here. All right? Let's see here. I think okay, here's Sarahi. Let me, if those of you that I name now would come up and get this. This is your math assessment, and I will finish taking attendance this way. And the rest of you can be dismissed if you got your thing. Samantha, Escadon, Carlos. There's Sarahi. Samantha. Shayla Hughes. Tiffany Lopez. Jonathan Martinez. Danielle Orta. Brianna.
Thank you.
Snyder. There you go. Brianna, wait a minute here.
So.
Yeah, but I don't see your. What's your last name?
Slaughter.
Oh, there we go. I was looking for Snyder.
Oh, okay.
Okay. Tori?
Oh, sorry.
Tori here? Okay. Yes? Yes.
Okay. On the quizzes, is there any way, because, like, I don't like how you can't see what you messed up on. Does that make sense? 'Cause
Yes.
on the homework,
You
I
sent me a
was-
note on that. No, you didn't. Okay, somebody did.
No, I did. About the homework?
Yeah.
It's not letting me, like, even see anything on it.
Yeah, you
Oh, I think
are.
she had that problem.
What's your name?
Slaughter.
Yeah. Were you doing it on Monday?
I did it yesterday. I was doing it yesterday.
Yeah, Monday.
Yeah, sorry.
That's right. Okay. Well, yeah, somehow, did you do it for a little while and then it kicked you out of it, or what happened?
It wasn't letting me, like, even look at, like,
But it
the
did give
question.
you,
A 5, yeah, I saw that on my grade. I
did
was
you
like,
get one question right or
I
something?
didn't even do a question at all.
You didn't even do a question? I know, okay. Okay, well, what I explained is their, Connect is headquartered in Florida.
Yeah, I saw something like that. On
Yeah, yeah, so I called them this morning and they told me they would let me know. They said, yeah, we do have technical difficulties, we're running off of generators. We'll send you, they're gonna send me an email when it's been corrected. And when that's done, I will send 6 of you a note
Okay.
and saying that I've extended, given you another attempt to do the homework, okay?
And I called them last night too. It took me almost an
Good, I'm
hour.
glad you called them. But yeah, but yesterday was just the wrong day to be doing Connect,
You're right.
okay?
So,
They lost their power, they had to come up on generators, I'm sure they had all kinds of problems.
yeah, they told me the same thing as you, so
Yeah.
just gonna wait
So,
for an email.
and you are trained?
Yes, sir.
Yeah, trained, so just expect an email for me. I mean, if it takes 3 days, it takes 3 days. And then I'll send you an email and say you can go do chapter 1 homework, okay? We'll give them as much time as they need, but we'll see.
Mr. Rick, is there any way that I can see which questions I got wrong on my quiz?
Yeah, that's what Brianna was just asking me. Let me just note that. I don't know. A question like that I can't answer off the top of my head. But let me note it. Every time I call in with a question, they always say, now, Mr. Rick, is there anything else I can, got any other questions? And I usually say, yes, I do, but I have to go teach a class right now. So I will call you back. All right, question. Can students, can students see what they got wrong? I may have it set so that you can't, all right? But what I do have set on the homework is that even after it closes,
You can go back and look at it.
you can go back and look at it for study purposes.
Right.
But what I'm saying is you can't do that for the quiz. I'll ask him, what are the implications of that? Why wouldn't I want you to look at that? I don't know. I think you're all getting different questions. I just have to philosophically think whether I want you to be able to see the
Yeah.
quiz after you've done it or not.
Well, my
You
only reason
obviously
is
want
just so I can see
what
I
you
need
missed.
to work on.
Yeah.
Because on the homework, at least you can see what you missed, and then you even have that second chance to correct yourself. But on
Right.
the quiz, it's just like, all right, you got your grade, you're done. So it's like,
And you don't know what I got wrong.
well, what did I mess up on?
Okay. Okay, well, I'll try to roll back around to think that through, maybe call them. I do know that because I have set the homework that you can look at it for study purposes, I think I'm gonna have a hard time extending it for these 6 people that need it extended. Because I've tried to do that in the past, and they said, you can't extend this because you have given access for study purposes. So they'll have to coach me through that.
Okay.
I don't know what somehow I'm gonna have to force it to let you guys do it again, but
Okay.
I'll work through that.
Thank you.
Yeah, you're welcome.
Sorry. On one of the days, I believe last week, I was absent. I have a doctor's note. Do I give that to you to not make it an absence?
So let's see.
It's right there, yeah.
You sent me an email,
Mm-hmm.
and I don't usually do this, but I put an E there, meaning basically I'm gonna excuse you for that day,
Oh, okay.
okay?
Okay.
So you don't need to, you sent me an email,
Okay.
and that's how I handled it, okay?
Okay, thank you.
You're welcome.
Professor,
Yes.
I wanted to tell you about, like, I have to drop this class.
Do you?
Yes.
Why is that? You're Lewin.
Yeah. It's because I found it, like, a soccer club from England. And
You what?
I found a soccer club in England.
Are you a soccer player?
Yeah. And I play.
Are you a
with-
professional soccer player?
No, not yet.
Not yet.
But like I found this club. So I played with Northwest Vista, and but I quit because of this class. So when I found this club, they told me that I need to show them some videos of me playing. And look, the only way that I can show them videos is if I go back to the soccer team here. I
So you
have
can
to
get a
go.
video.
Yeah. So
And you gotta get. Are you sure that's the only way? Now, is soccer more important than your degree? What are you working on?
like now it's history, but I would change it to computer science.
Now it's history.
Yeah.
Maybe you'll change it to computer science. Can you go to the NVC soccer coach and tell him your situation?
Yeah.
And tell him, can I just come?
It's
and-
because the practice is from 8 a.m. to 10, like
Tuesday and Thursday?
Tuesdays and so
Can't you just go to one practice and get the video?
I don't know.
I mean, you're not going to video every practice,
Yeah.
right?
Yeah.
So go to one practice and get the video. Think that through, okay? Okay. I'm just telling you. You do what you want to do. It's your decision. But don't just, kind of don't just drop this because of that, unless that is really what fits your plan. All right? If there's a way to accomplish what you need to accomplish, if you miss one class, you miss one class. Just don't miss a test. Don't go off videoing soccer during a test, okay?
Yes, sir.
All right? So think it through. And then let me know. I mean, I'm sure you've already thought it through, but I'm just giving you some more things to think about. Okay?
Yes, sir. Thank you.
Okay. And well, let me know. I think you can